So let's look at problem 12a in your notes. Waves in a string, problem 1. So an astronaut on the moon, where g is equal to 1.62 meters per second squared, sorry about that, wishes to measure the mass of a moon rock, so the mass is unknown, on that planet by observing a string vibrating in a standing wave pattern as shown below at the constant frequency of 60 Hertz. The vibrating part of the string is 2.1 meters long and has a mass of 7 grams. That's saying there's 7 grams for that whole 2.1 meters. It's not taking into account any other part of the string, like this part. It's not in that mass. Calculate, number 1, or A, the mass per unit length. So U is equal to mass over length. That is 0.007 kilograms, very important you're in kilograms, over 2.1 meters. So the linear mass density is 0.00333 kilograms per meter. B says find the tension in the string. Normally, we'd come over here and we'd say the force of tension up equals the force of gravity down, and we just use mg. But we can't do that here because we do not know m. So another equation we know is that the velocity is equal to the square root of tension over the linear mass density, square root of both. Well, we also know that velocity is equal to wavelength times frequency. Lambda frequency is equal to the square root of ft over u. That seems like we have enough stuff. The question is, what's lambda? Let's look back up here. We've got one wavelength right here. So from the start to here, so that's 1 lambda. And then we have a whole another lambda here. So we've got 2 wavelengths here. So we can cut that in half and say we have 1.05 meters per wavelength. So the wavelength is 1.05. The frequency is 60. We're looking for the force of tension all over 0.00333. I would square both sides, multiply, then cross multiply, and I wind up getting 13.2 newtons is equal to that force of tension. Okay, so let's go back up and see what it wants next. The mass of the moon rock. Now we come over here and look at our free body diagram, and we know that the force of tension is equal to the force of gravity on the moon. The force of tension is 13.2. The force of gravity, so let's see, that'd be the mass times gravity on the moon, 1.62. Remember, g on the moon is 1.62. So the mass is 8.16 kilograms. And then finally, what would the mass of the moon rock need to be to produce the first harmonic? Well, let's in our mind do some thinking. The first harmonic would look like this. So this length is 2.1. That's half a wavelength. So 4.2 meters would be lambda. We can do a couple different things, but let's see. We know lambda times frequency is equal to the square root of the force of tension over the linear mass density. We know that the force of tension is equal to mass times gravity over u. And so if we say square both sides, let's cross multiply. And then let's divide by gravity. Okay, so now we've arranged it so that we're solving for the mass. And let's plug in. The U is 0.00333. The lambda is 4.2. The frequency is 60. I'm about to forget to square. Squared all over 1.62, and that equals the mass. Math, and we get 131 kilograms. would be that mass. If you don't want to rearrange it, like I did, you can always just plug in up here and you can solve out for 131 kilograms. So let's take a look at 12b. A physics student observes a string vibrating in a standing wave pattern, as shown below, at a constant frequency. We don't know what that frequency is. The vibrating part of the string is 1.46 meters long and has a mass of 2.45 grams. So a couple of things. Notice we're in the third harmonic. So 2/3 of the length will equal the wavelength, because this is the wavelength, right? Another thing that I just need to add is, I don't have it on here, but it should say 3 kilograms. That's what the rock is. So let's do some calculations. The first one, calculate the mass per unit length. So mass over length. Make sure you've got it in kilograms, 0.00245 over the length, 1.46, so kilograms, meters. So U is equal to 0.00168 kilograms per meter. So that's linear mass density. The tension in the string. Well, we have two equations to calculate that. We could say velocity is equal to the square root of the force of tension over U. We don't know the velocity. We also know the velocity is frequency times lambda, but we don't have the frequency. We also know that the force of tension is equal to the force of gravity on that rock, whatever that hanging mass is. And this time we do have the mass. So let's use this. The force of tension is equal to mg. The force of tension is equal to 3 kilograms times 9.8. We are back on Earth, and that is 29.4 newtons. So that is the force of tension. The next one, C, says calculate the frequency of the vibrating source. Can't count because this is B, so let's go to C now. So frequency times lambda is equal to the square root of the force of tension over U. Frequency times 2/3 of that length, so 2/3 of 1.46 is equal to the square root of 29.4 over 0.00168. And when you solve this out, frequency will be equal to 136 hertz. And finally, D asks, the hanging mass required to produce the first harmonic. Okay, so the first harmonic, you will recall, is just one loop. So that's really half a wavelength. So it's going to require 2 lengths to make the first harmonic. 2 times 1.46, and that is 2.92 meters. Because remember, L equals 1/2 wavelength on that first harmonic, and that's where we got the 2. 2 times L equals this. So I'm getting that. So 292 meters, 2.92 meters. So D, we want to do frequency times wavelength is equal to mg, because the force of tension is equal to mg over U. The frequency is 136. The wavelength is 2.92. We just did that above. Mass is what we're looking for. We are on Earth, so it's 9.8, and the U is 0.00168. Do some math, and 27.0 kilograms is equal to the mass of the rock required to give us the first harmonic. Okay, so the big deal on these is identifying your harmonic, and from that information, transferring it into wavelength. You've got to be able to work in the correct wavelength. Also, being able to put these together is important. It allowed us to solve for mass, both on this problem and the problem before.